Hi guys, I'd like for you to find your packet and turn to this page in the packet. This was an activity that we did not get to do in the regular chemistry classes, but we got to do this mainly in the honors chem. And so if you're in honors chemistry, you can skip this video. For regular chemistry, let's have a look at this together. We've learned that the sun emits a mixture of electromagnetic radiation, and that's just simply waves that carry energy through space. There's all sorts of EMR, including gamma rays, X-rays, ultraviolet, etc., all those things we've talked about. And many of these types are emitted by the sun. However, most of what is emitted is UV, visible, and infrared. So here on your handout, you can see the visible range, okay? And so this is the violet light over here, close to the ultraviolet, and then the rest of the rainbow finishing in red light, which is right next to infrared. So you have the visible light, which is a lot of what comes off of the sun. 44% of what comes off of our sun is actually visible light. And about 7% is ultraviolet, and there's not a huge amount of X-rays or gamma rays coming off of the sun, so that's good. But you do have some ultraviolet, which is a bit dangerous for us and can cause skin cancer and that type of thing, so we have to be careful about UV. And then about 49% is infrared and with small amounts of microwaves and radio waves. Okay, but most of what the sun emits is ultraviolet, visible, and infrared. Okay, and the human eye detects only the visible stuff. Okay, and it's kind of an interesting idea to think about the colors that we see really just occur in our brain. Our brain doesn't know what to do with these wavelengths or these wavelengths, but if those wavelengths fall in a particular range from 400 nanometers to 700 nanometers, our brains generate colors in response to those wavelengths. And it's sort of an interesting idea to think about the colors that we see. There's not really a way to prove that the red color that I see is the same as the experience that you have when you see red. We might both look at something that's red and, we would both call it red, but when our brains see that color, maybe they get interpreted as a little, in a different way. And same thing with all of the colors. But, I tend to think we probably see the same type of colors because we have very, very similar brains and similar cells in our eyes. And so I suppose that we see colors in a similar way. But these colors are translated inside of our brains, and it's a response that our brain gives to these particular wavelengths of light. Okay, so the activity that you guys missed, that we didn't have time to do because we were going to do this on Friday, is I gave everybody something called a spectroscope, and a spectroscope has a prism inside of it. And kind of like what we talked about yesterday, if you look at sunlight through a prism, you get that full range of colors. You basically see something, you see something like this right here. So you see a full rainbow of colors. So I gave everybody a spectroscope so they could experience that. And we call sunlight white light. Okay, but it's really a mixture of many colors like we talked about yesterday. Okay, so people got to do that, and this whole variety of colors is called the spectrum of sunlight. Okay. Now, when the students came back inside, they didn't get to color the full rainbow because we didn't have time, but in years past I've had people color what they see in this space. And so if you want to, you don't have to, but you could color in a full rainbow, starting with red on this side, right? And red is kind of going along 700 nanometers, and I'm not sure exactly where to stop. And the scale is reversed from this picture, so here's 700 nanometers. Right about to 600 nanometers, it looks like, is where you start getting some of the, the orange and yellows, right? And So kind of in here, it's just full colors. And then somewhere in here, you start getting into the oranges and the yellows and that type of thing. And so let's see. Then just past 600, it's green all the way up to about 500. Let's see, so a nice green, maybe something like that at first. Got green kind of going all the way up to 500, and you get the full rainbow of colors. I'm just going to go ahead and finish it up with some of the blues and violets here. Blue starting just past 500, and then close to 400, you got the violets. There we go. Come on. All right, so in years past, we've got to do that and spend a little time doing that. Okay. Now, there doesn't seem to be any gaps in here, right? It's a full continuous rainbow, or so people thought for a long time. Somebody had a really good prism, and they had some really bright sun rays in a dark room, and they were looking very carefully at the spectrum from the sunlight. And what they saw when they looked really carefully is that there are specific gaps here. Well, this is not exactly to scale, but somewhere in here and here and down over here and here. And that was kind of mysterious to them, and there actually are some other gaps in there. And what they realized is that these gaps correspond almost exactly, actually not just almost exactly to the wavelengths that we see when we energize hydrogen. And it seems to be the case that hydrogen in the atmosphere of the sun is absorbing those particular wavelengths of light. And so that's kind of funny. And that's how we know actually that most of the sun is hydrogen. These particular colors of light are actually missing from sunlight. And that's because there's hydrogen in the atmosphere of the sun absorbing those specific colors so they don't show up by the time they reach Earth. So that's kind of interesting. So these colors of light are the colors of light that hydrogen emits when it gets energized, but it's also the very same wavelengths of light that hydrogen absorbs in the atmosphere of the sun, and that lets us know there's lots and lots of hydrogen in the sun. The sun is mostly made of hydrogen. Okay, so let's go back to the packet here. And when we turned the spectroscope and had a look at the fluorescent lights in the room, I've forgotten the exact colors that we saw there, but there were only a few specific colors being emitted in the room. And I think there was a little bit of orange in there, but no yellow. And some blues, maybe a green, forgotten exactly, but there was like 5 or 6 just very specific colors of light. And that's because in the fluorescent bulbs in the room, we don't have sunlight, we have some elements inside of the fluorescent bulb, and those elements, when they get energized, emit very specific colors of light. Okay, so that at first might seem very strange, but it's kind of similar. It's exactly the same thing as hydrogen only emits 4 specific colors of light. Sodium emits its own specific colors. Tungsten emits a lot of colors. And this is almost as good as sunlight. If you think about it, it's almost a full rainbow. And so it turns out that using tungsten in light bulb filaments in the past was not a bad idea, because you almost get a perfect rainbow. And so you have a very, very nice natural type of light that's similar to sunlight. Almost as good as sunlight. You're getting a lot of colors in there. Compared to hydrogen for sure, and compared to neon, which would be terrible to use for everyday lighting. It's just a bunch of yellows and reds and oranges. Tungsten, you get a nice palette of colors. Okay, so let's go back to the packet and kind of finish this up. Final reflection question. The reflection question was basically, what do you think is happening inside of these fluorescent bulbs? And the idea is the fluorescent bulbs contain specific elements. And so we're only getting specific colors of light. Only a few specific colors of light.